Welcome, class, to Engineering 2103 Statics. This is the Week 2 Monday lecture on force vectors. Share the screen. This is the lecture, or the Monday lecture on force vectors. So we have scalar quantities and vector quantities. The scalar quantity is magnitude only. Vector quantity is magnitude, direction, and kind of application. And in effect, what that does is it gives you a sense of the vector. And so we have point of application, vector A, and a bar across to indicate a vector quantity. If I didn't have this, I'm saying it's a scalar quantity, and I want to make sure I'm clear that it's a vector quantity. Then we're going to have to give a location, which is going to be some angle with a reference axis, and this is typically the x-axis. So we reference this vector with a direction and an angle. Vector operations, you're all familiar with these. You can be multiplied, divided. We understand what happens. If it's multiplied, its magnitude is increased. If it's divided by a scalar, it's decreased. And if you have a negative direction scalar, it just changes direction of the vector. There are two ways we can manipulate vectors using vector operations. We can use the parallelogram law, where we vector A and vector B, starting from the same point, we complete parallelogram. Resultant is that diagonal across the parallelogram vector quantity. We use a triangle rule, A plus B. So here's A plus B, and the resultant goes from the beginning of A to the end of B. Again, you've got to use trig law of sines, law of cosines to do these solutions. Typically, we won't work our problems using the vector solutions. Got another way to do it. It's a little bit more sense and much easier in most situations that we have. I'll show you those. So in a statics problem, it's very common to do really two things. Is given a force vector, force 1 and force 2, acting on a support. And as an engineer, I want to design that support. Well, given two forces, it doesn't tell me what I really need to design. I want to know what the total force is acting on here. To know the total force, I can design this. And so we have basically two components of forces, or two forces. We want the resultant. Okay, so here's the resultant. What this means is I can get rid of these two forces. There's one force on here, and that's truly what's going on, that support, that one. And I could use the vector method to solve, but show you what happens when we want to do that. So I put my other camera on. If I have multiple forces, probably more than two, even two, but only more than two, show you what happens if we do that. Basically, what we want to do is use components here to show us a system. Basically, what we got, we have, to summarize, we have forces, and what we want to know is what the resultant is. We also have forces, and we can resolve these into components. So I'm going to give you a force 1, force 2, and 3. And what I want to do is get the result. I want to add these forces together. So if I go back to vector operations, I can use triangle rule. I can take, again, I got 3 forces, so I got to do this incrementally. So I'm going to take F2, add it F1, and what I can determine is a resultant one. Well, now what I have to do is do the same thing again, except add a force 3 to this resultant one. So here's force 3. And now what I do is have to have the second result, which is the total. So this is resultant 2, which is the resultant R1 plus R2 and F3. If I had a fourth force on there, I'd have to repeat this again. Oh, this is too cumbersome. Okay, we just simply want to do this. And so what we want to do is use components. Very simply, we want to use components. And let me show you. I have a axis system, y-axis system. X-axis, and here's my y-axis. I have a force F1, force F2, and I will have a force F3. Components. A vertical of the x-axis for F1 is F1 x. Projection over to the y-axis is F1 y. For F2, again, down to the x-axis. Right. This is F2 x. Got this over here. This is F2 Y direction. Okay. F3, projection onto the x-axis is F3 X. Projection to the y-axis is F3 Y. So I want to sum forces in the x direction. I have F1 X. So we have to be careful now in directions. We're adding and subtracting now. And F2X is in the negative direction. So that make sure we get that negative sign in there. That negative sign, the problem is wrong. So minus F2X. Here's F3 plus F3X. Do the same thing, forces in the Y equals F1 Y. F2Y plus, there's F3Y. Again, you'll look, this is in the negative direction. This is minus F Y. Problem with some numbers on it. Resultant we're going to just sum forces in the x and sum forces in the y direction. Okay, as you go through this, what the resultant. So sum of forces, the x plus sum of forces y. So what we end up with is something that looks like this. It's going to be sum of forces in the x. We have sum of forces in the y direction. And the resultant and is got a triangle that we're solving for. So the force resultant then is just going to be square root force resultant in the x direction squared. It's the force resultant direction squared. Root of that quantity. So when I sketch this, my XY axis system, I sketch this. Suppose this is my resultant, and you know this angle theta. So theta and is going to be equal to the inverse tangent force resultant y direction divided by the force resultant in the x direction. And theta is always measured counterclockwise with respect to the x-axis. Okay, so this is counterclockwise with respect to the positive x-axis. Well, an example with some numbers. So this is example 2-3 in your textbook. We have it's like some kind of a support device that's into a wall system. We have two forces, F1, 150 pounds, angle is 60 degrees, and we have a force F2 is 375 pounds, 5-degree angle. We want to know the resultant, and with the resultant, we also want to know the direction counterclockwise with the x-axis. So, 1 of x is 250 cosine of 60 degrees, 125 pounds. Cosine adjacent. S of y, sine function, so it's 250 sine of 60 degrees, 217 pounds. F2 of x is 375 cosine of 45 degrees, 65. F2 in the y direction, y component is directed in the negative direction, so that's going to have a minus sign, minus 375 sine of 45 degrees, minus 265. We sum forces in the x direction, so it's going to be the 125, 265, 190 pounds. Some forces in the y direction, 217 pounds. And then it's minus 265 pounds. It's minus 48 pounds. With some forces in the x, 90 pounds, some forces in the y, minus 48 pounds. So the resultant, the square root of the forces in the x squared, which is 390 squared. And then we have minus 48, plus minus 48 squared. Square root, there's a square root 154,403. This is what it comes out on your calculator, 92,943. If you write this as the answer, I'm going to say, so you measure this out thousandth of a pound. You're going to say, well, no. And we were just getting probably to the nearest pound. Why did you write this answer? This goes back to chapter 1, significant figures. This is false accuracy. round 3 places. So we have 3 significant figures. So the answer is 393 pounds. This was a test question, and you wrote this. I mean, everything's correct, except you're telling me this is the answer, and it's not the answer. The answer is 390 pounds. I might take a point or two off. Definitely would take something off in the beginning. And as we go on, of course, it increase on terms of what the negative value would be on this. Okay, so the answer is 393 pounds. I want to plot this so I know where this is at. So here's my, just roughly, when I do this, my x, sum of forces in the x was plus 390. So we're out this way. The y is negative. So I'm in this quadrant. So I calculate somewhere out in here. I can sort of roughly plot it as a resultant. Theta is the inverse tangent of 48 over 390 y dx. And so 7 degrees. And so you write your answer, 393 pounds, theta is 7 degrees, and this is how you sketch it. And this is incorrect. Angle is measured clockwise from the positive x-axis, which means this is the angle. Not this. And so the angle would be where you're at, how you calculate it, if it's over here or over here. So this would be the 360 minus this 7 gives us this angle here. So it's 360 minus 7. The theta this way is 353 degrees. So this is your answer. We highlight it, set it up in nice, neat engineering format, nice sketch of the problem, and we sort of go there. Okay. This is problem 231 in your textbook. I don't have the textbook problem. This was another item I had to try to get in here and reference back to it, and I didn't copy it on some paper in the notes. But this is a sketch of the problem. This is a large, nice colored sketch in your textbook, and it's being pulled by 2 tugs, A and B. And the force in A is 2 kilonewtons, and it's acting at a 30-degree angle. F sub B is unknown. F sub B in just a second. But we know this. We also know that the tug is going to be moving along this x-axis. The resultant force is going to be in this direction. We want F sub B to be a minimum value. Minimum value. So we have 3 forces. We put this in a, actually we know 2 things. We know this direction, and we know this force. So I'm going to use a triangle in this case, the unknowns. So here's my F sub A, and I know the resultant's going to be along the x-axis. Here's my f sub b out here, and I want that to be a minimum. Okay, so this is sort of the sketch of the problem looking at. So this ends up being the resultant force, okay, along the x-axis, F sub r. This is the force, the first tug, Kn. So know this force. And F sub b has to sort of close this triangle because we know this, and the third force has to close this triangle. So if F sub b is out here, the F sub r resultant force extended out, F sub b be here and gets its minimum. It's greater out this way. This is less. If I drop a vertical, this is actually the minimum value here. Okay. It's the minimum value. At any angle, sub b becomes larger. This is the minimum value. So that is a condition. Here's my triangle, 30 degrees, Kn here, F sub b and resultant. So sine of 30 degrees is equal to opposite F sub b or hypotenuse. Hypotenuse is 2. So F sub b is equal to 2 sine of theta a kilonewton. F sub b is 1 kilonewton. And then F sub r would just be 2 cosine of 30 degrees. 1.73 kilonewtons of r. So believe it or not, you could have this tug pulling this way. One kilonewton, and the barge would be moving horizontally along this x-axis, and the force would be 0.73 kilonewtons. If we go back, and this isn't a minimum, it's something else. In other words, if F sub b is somewhere out here, I'm going to suspect that this isn't going to be along the x-axis. Okay, it's going to be probably in this direction, in the geometry of the situation. That's a clever little problem. It's a little thought to get through it, I think. But that's sort of what we're looking at. Go back. Go back to notes. I'll do this example probably starting next time. another example out of your textbook. A few more problems. We'll sort of stop at this point and continue on with the lecture on Wednesday then.